In this video, I'm going to describe some of the components that are used in the industry to help scale web application. A lot of these techniques can be used not only for application related to like website, but also if you have like a voice telephony application or video conferencing application, the concept is similar across the board. I will use an example of a very simple web application, which is going to be a simple application where a user can upload photos and then retrieve this photo later. We're going to start with a very simple implementation and gradually explain each design and see what would happen and how we would be able to scale it from an application that can handle, let's say, 500 users. How can you make it so that now I can handle 1 million of users? Okay, so before I dive deeper, let's kind of talk about what does that mean, a scalable and distributed system, so that we can be on the same page. Usually an application is very simple. You have a user, and then you have a network, which is usually the internet, and then you have a web application hosted somewhere that the user can request data. That's pretty much as simple as it is. User, and then a network, and then some application that is connected to some data store. But there are a couple of things that we need to take into consideration when we're building those web applications, as far as making it so that a lot of people can use the application at the same time. Some of the things that we need to take into consideration include availability. We want the application to be available 24/7, because certain applications, if they are not available every minute, the company that hosts that application is losing a lot of money. Think your favorite shopping store, or let's take a favorite like Amazon or HomeDepot.com. If their web application were to not work for, let's say, 1 hour, they probably would be losing in the neighborhood of hundreds of thousands, if not millions of dollars. Performance. Performance is another thing you need to take into consideration when you're building your web application. I think now with the internet being fast, people don't have the same level of patience they would have had, let's say 5 or 10 years ago, where they will not wait for photo to load, they will not wait for video to be buffered. People lose very patience. If they go on your website and your website is not loaded in the first second, they are already clicking out and then go on Google and search for another service or another website that offers the service that you have. Reliability. Your system needs to be reliable. What I mean is that it has to be not only be available. If, for example, a user saves their data and then later come to read that data, it should be reading the latest data, so it doesn't have stale data. Scalability is another thing we need to take into consideration. If you have a system, the system needs to be able to not only scale when demand is high, it should also be able to scale down when demand is not as high. Maintainability. As your system grows, you would require more engineer to maintain the system. And if your system is complicated for engineer to work on, it will really impact the performance. Not only the performance, but it will really have a negative impact, because then it will cost you more money, because then you have to hire more engineers to get the system running. Finally, another thing to take into consideration is cost. As your system becomes bigger, you need to buy bigger server, hence you need to pay people more money to maintain the system. So the simpler you can get the system to be, this would make it so that you don't have to spend extra money where you don't need to be spending that extra money. Okay, now that we talk about the components that are important in a system, I'm going to use a very simple example of an application where a user can upload their photo, and then the user can download this photo later on, can retrieve this photo later on. So let's take a look at the initial design. Right, in this initial design, we have this is the server. The server is listening on port 80 and port 443. Usually we use port 80 when we want to send an encrypted message, and port 443 to send encrypted message. But for now, for simplicity, we have this port open. So a user can upload an image. Once the user uploads the image, the server takes the request and eventually save the image into some type of database. This is a very simple application. And then once the user finish upload the image, the user can easily retrieve the image on an alerted time. As you can see, this is a very simple application. There's nothing that complicated. Sometimes in that web server, you can have like Apache or Nginx. So these are applications that are used to listen for requests over HTTP. They take care of taking care of all of the protocol-related things. And then once they get the request, they forward it to a web app. I mean, the web app would either expose the web app would expose certain endpoint, and then based on the endpoint, like for example, if you do dash upload, it's going to go into the upload, and then that retrieve is going to get into the retrieve. Simple application, nothing complicated. First, let's kind of take a look in terms of what are the limitations of that first application. First off, the server has a limit in how many concurrent connection that they can handle. Usually, Apache without any configuration can handle 500 concurrent connection. You can still configure so that it can handle way more concurrent connection, but usually there is a limit in the number of concurrent connection that the server can happen. Concurrent connection mean there are at least 5 or 7 people at the same time that are either reading or uploading data into the server. So this is the first limitation. And let's kind of try a way to see how we can handle this limitation. We are going to now go into one way we can do it is by breaking our application into services. Services, or sometimes they call it microservices, are endpoints that are or application that specialize in a specific task. For example, now we're going to break them in application into 2 services. One service would be focusing on image upload, and then another service is going to focus on image download, like retrieval. By doing this, many things that we can save ourselves. First, usually writing to disk is slower than reading from memory. Usually, if you need to upload image, eventually this application, this endpoint, the image upload, would get your request, and it will send the request to the database, and eventually the database would have to write this information into hard drive. And this writing into hard drive is way slower. So because of that, by having a service that is on its own that takes care of writing the data completely separated from reading the data, we can make it so that if there is like 500 people that are writing data, it's not going to block people who wants to read data because reading is faster. The other version of the application, if there are like 500 or 600 people that are currently uploading into the service, and then there is another person in the queue that needs to read, this person would have to wait a very long time because doing those concurrent connection, that last person who wants to read would be waiting for the people that are doing the writing. Now, we increase our server capacity because read is very fast, right? Maybe you can handle 1,000 people reading at the same time without any issue. And then for the image upload, now you can have these people take care of the upload. So the first version, by breaking the application into services, we reduce the load, and then we make the application more manageable. Usually you could have also a piece here that's a load balancer, but I will talk about load balancer a little bit later. The load balancer would be a front when the requests come in. It can know if you need to send the request to write or if it needs to send the request to read, but we're going to leave this to later. So First problem, let's go back, quick review. We have one server that was doing both the reading and the writing into the database. Now we split the application into service where one service specializes in getting requests related to write, and another service is specialized in requests related to read. So now let's keep moving to the next layer. What happens if one of these services goes down, or if this goes down? Because now we only have one on each instance. And I don't know if you've been in that situation, if you're driving late at night and then your tire explodes, and then it's 2 a.m., 3 a.m., and then you have your family in the car, and then you don't have a spare tire. So to solve this problem, we need to come to a concept called redundancy. Like, redundancy is very simple. Pretty much have at least two of your services that are running at the same time, so that if one of them were to stop working, the second one can work. For redundancy, there are many ways you can go about it. But again, usually there would be a load balancer here. But for simplicity, since I haven't talked about load balancer, pretty much when a request comes here, the request go into the load balancer, and the load balancer pick which service that needs to get the request. Same here, there would have been a load balancer here. But again, I haven't talked about the load balancer. For simplicity, I just put two servers. So redundancy is the capacity so that if one service stops working, the other one continue working. That's the best way you can prevent your application from being available. So you're going to increase availability by having at least two services that is serving the same type of request. Same way for the database, you have two databases. So usually one database will be the primary. So every request comes, and then the first database take care of the request and then serve the data. And then if something gets changed into that database, then there is another copy that is being done in the background so that the data can be in sync. And usually it's good to put this in different geographical locations. For example, this one can be in east, and then this one can be somewhere in west. Mostly so that if there is a flooding in one of the data center, your data is still there and then you don't lose all of your data. So this now, it's a way to increase availability is by having redundancy, which is pretty much have at least two copies of each service, or have at least two copies of your database. And one database will be the primary database that is receiving all of the requests. And in the background, everything data gets changed. There is a copy of it that keeps being copied somewhere far away. Two services now mean you can get more concurrent connection. So instead of 500, now you can get like 1,000. So it's not exactly 1,000, it can be way more. So, and then the read can happen, again, same way. You don't have to wait. And then if one was to go down, the second server or the second service would help. Why would one go down? For example, the hard drive failed, someone disconnected the server, there is a flooding in a part of the town, like there's a flooding in, Atlanta, and then your server is in Atlanta. So usually you need to make sure that your services are in different geographical locations so that you can have more flexibility. Let's turn now into a third concept in distributed system that is called partitioning. So earlier when we were talking about the data, right, we were saying how user reading data can be slower than writing data. Another concept that you can do with your data is called partitioning. What does that mean? Partitioning means instead of having all of your data in one database, you have your data such a way that a portion of your data is in database A and another portion of the data can be in database B. Why would you want to do that? Well, you do that to speed up query requests. For example, if you only have one database and all of your data is on it, and then you are doing a search, the search may have to traverse the entire database before they can do the result. However, if you partition your data such that, right, you can partition it in a way so that every client where the last name start between A to, let's say, to M, their data is going to be in database A. And then every client from O to Z are going to have their data in database B. Just by doing this, it makes it so that your database is not working as hard to serve all of the requests. You may need to have some application logic that can figure out which database the data needs to be going into. And then once you know what database is going to go into, so you want the data in whichever database that it goes into. This would require a little bit more hands-on because you need to figure out a way to partition the data that makes sense for you. So it can be a hash function, it can be other way you can partition the data. But doing so would give you some speed advantage because now all of your data is not in one database. Your data is across multiple databases. And because it's across multiple databases, it just makes it easier to find because now you shrink, the amount of data and the amount of space to search. And at the same time, because of redundancy, you also need a copy in different geographical location because you want to be sure that if one of your database were to go down, the primary one were to go down, then the secondary one would go and take up the slack. And same way, if one primary goes down, the secondary one would go to take up the slack. We talk about partition. We talk about having multiple services, redundancy. We talked about how you can have a service and then instead of having one application. One thing I forgot to mention earlier, so I'm going to recapitulate. This initial design is where a lot of big companies started. You shouldn't feel intimidated if this is where you start. You have to understand the advantage of having a simple design like this. It is very easy to deploy. And also with this design, you can have your first idea out to the world and start earning money. Right? You can start earning money because your design is already out and it's very simple. They usually call this type of design a monolith. But a lot of big companies, Netflix, Amazon, Facebook, they all started here. They did not do that level of complexity until they either have the money or they have the resources to maintain multiple copy and multiple data. So most people are probably going to start here, start having some customer, start earning the money, do proof of concept, and then when they start getting a load, then they can go to the next level to make their infrastructure better. So far we talked about partition, we talked about redundancy, and we talked about services. Now let's dig into way that we can improve our application so that people can get access to their data faster. If you look across the internet, most of the application that you use, it's pretty much here a user, right? It's pretty much a user via the internet that's hit a web app, and then the web app connect to a database to give the user back the data. Think about Facebook. You save your data in the database, and then later on, you read that data, or a lot of other people read that data. Think about Amazon. You have all of the data related to product, and then those data eventually get put into the database, and then someone else in the future can come in with the data. A lot of applications use that pattern. They just let data store. So one way we can improve performance is to optimize how we handle the data, right? So it's pretty much a bunch of consumer that's trying to read their data. And if we can optimize the time that it takes for these people to get their data, we can have a high level of speed. In the rest of this presentation, I'll share some idea on how you can optimize data retrieval, because this is very important. Not only data retrieval, but also how you can optimize data when you're saving your data. So there is a concept called cache. Cache, what is that? Pretty much a cache work by saving a portion of your data inside of your services so that before the service go to make a request into the database, they look into their internal memory. So for example, inside of this server, you can put a cache. A cache is just asking the server to use some of its memory to save their data. Usually it's a key value pair thing. So you have a key and then a value would be the data. So we use the cache to do that. Conceptually would be like the same way if, for example, you are an electrician or you would have a car that have a good portion of your tools, you cannot go inside of a house with your car. So you get a toolbox. So the toolbox is a cache. In it, you put the tool that you're most likely going to use. So you look at the tool, you say, hey, do I have my tools there? And then if you cannot find it in your toolbox, then you go check in your van outside. And if you cannot find it in the van, then you have to take a trip to Home Depot, which has way more. So as you can see, looking into your toolbox very fast. You just look into it. But then if you have to look into your car, you have to get out of the house, walk into your car, and then look for that tool. It takes longer. And then if the tool is not in your car, you have to drive to Home Depot, get the tool. So it takes way longer. It's the same way for cache. Usually the cache are in-memory cache. The easiest version of cache is just having it in the memory, and then the computer just read it. So a concrete idea would be this first version where this is your application, right? This is the application. So the user made a request, and then the request node check its local cache before querying the original data. So you made a request for the user, for example, give me my photo. First, the app would check, hey, is this photo in my cache? In my cache, maybe in memory. If it's in the cache, you just return it to the user. But if it's not in the cache, now the app has to do a network call, which takes a lot of time, get the data, right? Get the data from that big data store. And then once he gets the data, he would take that data, put it into the cache, and then serve back the data to the user that asked it. A network call can be very expensive. It doesn't happen, it's now you have to leave your data center and then traverse wire. It's not instantaneous, but it's way faster to just read, magnitudely way faster to just read the cache from your local computer. So, but now, remember earlier, let's put a load balancer here. Well, usually we're going to have a load balancer, LB. Remember earlier I say for redundancy, you may have to have multiple server, right, that has their own hardware. So now you have to take into account that you have each request node will check its local cache before requesting the origin. So you have your app, right? This is the app. Those are the app. And then when the request goes into the load balancer, any server can serve that request, right? When the requests go, and then that server that is serving that request will check its cache. And if it's not in the cache, then it's going to get to the database, and then the database will return it, and it'll put it in the cache, and then return it to the user. So now you need to be smart, right, with your load balancer, so that if the same user is requesting the data, it doesn't go to another server, because that other server may not necessarily have the data. So because of that, you need to spend some time deriving some extra logic in your load balancer, either session, some hash algorithm to figure out which one of those servers I should, they usually call it sticky session, which one of those servers I should send the request so that all subsequent requests goes to the same server for that same user, so that you don't have a lot of cache miss. Cache miss is when you look for the data in the cache, it's not there. So now you're gonna have to spend time going to the network. So, but if you ensure that the load balancer have the proper logic so that each user is sent into the same server that is serving them, unless the server goes down, then that's a different situation. If you do it like this, then you're ensuring that you're not going to get a lot of cache miss. And this would improve your situation like very well. There are other way you can do cache. Remember the earlier version, I'm like each server has their own little cache, but there is another way. It's called a global cache, right? For it, each request node will check the global cache. And then if the data is not in the cache will pull the data from the origin, then add the result to the cache for future requests. So instead of having a shared cache here, each server goes into their own local memory to look for the data. They use a global cache, right? A global cache might be in a data center, a part of memory that is very physically close to those servers so that they don't have to do a network call. You have to ensure that the time it takes to call your global cache is insignificant, in the sense that if it's less expensive to just go get the data because the network, the network is very fast, then it doesn't even make sense to have a global cache. But most of the time, they usually make the global cache to be so close to the server and all of these other virtual machines are so close to it that it's way faster to just get the data into the global cache. What problem does that solve? That solves the problem where earlier I said you have the load balancer. The load balancer needed to have some sticky session or some extra feature so that when a user make a request, that user is all of the subsequent requests from that user, it's always gonna get to the same server. Now you don't have to worry about that, because if the data is not physically in the server's memory, they're going to check in the global cache, and this global cache is shared. And also in this version, the global cache has extra logic so that the global cache take care of requesting the data into the database, right? DB. So the application is not worried about that. If the data is not into the database, the cache will go ahead and take care of the logic of requesting the data and then figure out how to load the data or what data needs to get out of the cache. There's something called cache eviction. It's a complicated algorithm. Not complicated, like there are ways you can make your cache so that it knows which data or which things can be kicked out, like least recently used or most recently used. There is another pattern where you have a global cache, right? For each request, the request will check the global cache first. And then if the data is not in the global cache, then the request node will retrieve the data from the origin. So earlier, the logic of retrieving the data was the responsibility of the global cache. In this version, the responsibility of getting the data, the logic is going to be inside of your app. The many reasons why you might do that, for example, maybe the global cache has, let's say, a very popular file that is very big, where a lot of people are going to use it, but then data that are not accessed all the time, we just dump it into the database. I don't see this logic being used that much, so I don't necessarily have a huge case for it, but there might be a specific use case where they just have a global cache, and then the responsibility of getting the data is the responsibility of the app. I just have not personally used that pattern. Now, we're going to talk about another one, which is the distributed cache. This one's a little bit more complicated. Personally, I don't have experience doing this one, but this is this one. So each request, the node check the cache based on the item key using a preferred consistent hashing algorithm, then the data origin. So pretty much, you have a load balancer, right? And you get a request, but then based on some hashing mechanism, it will know which one of those which one of the copy of the app contains the data. And then based on the location of the data, then if the data is nowhere in any of these apps, then it's going to check it inside the database. So the big database is going to be split into multiple portions that can fit into each servers. And then when a request comes, the load balancer would know which server has a higher probability based on caching where the data is, and then it sends that request to that specific server. And then if that specific server don't have the data, then the server can go and fetch the data from the database and save it in its local cache. This version is very complicated. I've never used this before. So maybe we have some proper use case. This idea of splitting the data. So this is what's going to happen is that let's say this node goes down, then you need good logic to kind of like handle a situation like that. Because, you need to figure out which portion of the data need to be loaded, right? Or at least which portion of the data is no longer available. But I think probably there is a huge case for it. It's just that I personally never had been in that situation where I take my data, split it into multiple pieces, and then put each piece in one of the servers, and then have that server be the authority of that, portion of data. So we talk about distributed cache, but now let's talk about some other hardware that you can find in a distributed system that can help speed up your application. So this time we're going to talk about proxy, right? So what are proxy? Why would you want to use it? So pretty much a proxy is another type of server, right, that you put between your requests. They can do a lot of extra things for you. For example, when a request node, right, let's say this is the client said the request, and then the request of the data is not in the client cache or the client doesn't have the data, instead of talking directly into the database, right, you can add another middleware like a proxy. Proxy can do things such as if all of those clients are requesting for the same data, instead of each one of them being served by the database, the proxy can take all of their requests, read it, and then realize, oh, these are all requesting the same thing. Instead of having 3 requests going to the database, that was going to be three different, search. Now the proxy would collapse that data, send only 1 request to get the data, and then when the proxy get that value, it will reply back to all of the other node that are requesting the data. That's one way proxy can be helpful. So far, a lot of the piece that I was showing was related in terms of speeding up data access, because earlier we see like most application, it's pretty much people getting data or people saving data. There is one technique that I wanted to kind of quickly touch. It's not complicated, but it's very simple, but it also can really help speed up your data. It's to index your data. Indexing your data is allow the database to, it's you trading up some extra space on your database so that you can have extra speed. Extra space in terms of like memory or in terms of hard drive. Pretty much when you save your data, right, you can create an index. An index is the same way when you have a book. In the book, if you go in the back of the book, you look for a word, and then the word will tell you which page number this word is repeated at. It's a similar concept for an index. Usually when you create an index, you tell the database which column, that this index will be at. Maybe you can say it's indexed so that by people's name, right? So if you're looking for a person, instead of going line by line looking for it, if you know there is an index that have the name alphabetized and then the location of the data, first you look at the index and you're like, okay, it's quicker, way quicker. So it's hard for me to explain, but it's one of those ways that works that can substantially improve your performance. The easier way, like I said before, the easier way to understand index is to take any book and look at the back of it, you will see something that says index. And if you look at the index, you will probably see that the index is alphabetized. And then you look for a specific keyword that you're interested in, and then it will tell you the list of pages where this keyword exists so that you can quickly search. So it's the same thing for the database. They are very easy to create, but it's one of those things sometimes people forget if you're not really have a deep experience in database. And then once you put the index, you can see your query speed become exponentially faster. And also what you would realize is that you have to give some space, right? So it's going to be, if you see index for table, right, you're going to have the data, and then you're going to have the location, right? You're going to have the, similar in the book, you're going to have the word, then you're going to have the page number. Okay, we've been talking about many components, but there is a very important component that I have not yet had a chance to talk, and this is load balancer. One component that we haven't had a chance to talk about that I say I would touch on is load balancer. Load balancer are a very important component in a distributed system. What the load balancer is, it's the endpoint that the client would send requests to. So when the client sends a request, they don't usually pick the server that the request is going to be forwarded to. They usually send the request to the load balancer IP. So the load balancer would get the request, and then based on some algorithm, it would pick the server to forward the request to serve the request. Load balancer does a lot of things beside that, but a few things they do, they help with CLS handshake, and also they help with making sure that the load, that one server is not being overwhelmed with all of the requests. For example, the load balancer may choose the server that is going to forward the request based on different aspects. It might be based on the token. Let's say if the load balancer has the opportunity to do sticky session. So if a user always sends a request, you want that same user to always be sending requests to that server that can serve it. For example, user A might be assigned to server, request A might be assigned to node A. So every request that comes from server A is going to be routed to node A. So while this is not an aspect, but I'm going to quickly touch on this. For security, there's something called CLS or SSL, pretty much when data are encrypted. So one way you go about it is you do key exchange and all those things. The load balancer can help with that. Sometimes when a user sends the encrypted data, the load balancer would take care of making sure that the data is decrypted correctly, and then the load balancer can then forward the request, maybe unencrypted, to the backend service. So load balancer can choose server based on their CPU utilization, like if a server has a high CPU spike, so the load balancer can be like, okay, let's take the server that has the less CPU utilization. Sometimes the CPU utilization can give you a hint on how much work a server is doing. And then this can make it so that the load is distributed equally across all of the servers that are behind the load balancer. So if you have another server here, right, you can attach. And there is a lot of logic to figure out how to add user to load balancer and remove user to load balancer, but I'm not going to go that much detail into this. Load balancer can get complicated in a sense that sometimes one request can go into the entry point, and then you have to contact another load balancer. A concrete example would be this system. So usually this part is a private network. Private. So usually the request would go to this load balancer, which is have an external facing with the internet. And then that load balancer may want to contact another load balancer that is internal. Maybe you're trying to contact, maybe that load balancer is connecting with multiple services, right? Maybe you have service A, which can be served by this. Maybe this is the service that where you write to the database, and maybe this is a service where you read data from the database, right? So now when the request go, it goes to another load balancer, and that load balancer would probably have a cluster of server behind it. So this can get complicated as you need. Maybe you need different load balancer if you're in different region. You're traversing from East Coast to West Coast. It's going to be one load balancer to another load balancer until the request is hit the proper server that can serve your request. The last piece of component that we're going to talk about are called queue. Queues are a very important concept, and it really helps speed up your system. And not only speed up your system, it make it so that your system work asynchronously. By asynchronous, that means you can submit a task to a computer. While that task is happening, you go do something else, and then you periodically check if the task has been completed. One way you can do that, there are many ways you can do that, but queue is a good way to implement that. But first, let's go into this. So see, in this example, each client waits for response directly from the server upon completion of the task. So the client A might have a task, and then you give the task to the server. The task might be to write to a database or to write the image earlier to a database. Remember, usually it takes way longer to handle write than it does to handle read. So if every time you send a request, the client is waiting for the request to get back, the client is in a blocking state. So the client sends the request, so client, and then this is the server, right? It sends the request to the server, right? While it sends the request, the server go and do the request, and then after the request is completed, then the server reply back to the client, and then the client can go to do something else. So this is time going by. So with this way, you are not wasting, but this time when the client is waiting, the client could have been doing something else. So that's this idea where we have queue. So here's how it goes in the second version with queue so that you can have a proper understanding. So here's how you would implement this with a queue. Instead of sending the request to the server and then wait for the server to complete his task and then get back to you, you can have a queue. So what you do, when a client sends a request to rewrite something, they would put it into a queue as a task, right? And then the client can go and then usually when you say that a task, we usually reply back to the client with some task ID, right? Task ID. It can be any type of ID, but some type of ID that the client can use later on in the future. So once the client, right, add something in the queue, he gets a number or some identification, the client can go and do something else. Something else might be call another service or write something else. And then periodically, the client can get back to the server and ask it, hey, what is the status of that task with the task ID? And if the task ID is have the data, then it will reply back to you. So the way it usually do, you send the request to the queue, right? And then this is the server. The server is reading from the queue. And anytime there is something to be done from the queue, the server would take it, get it done, right? And have it ready. And then once it's done, sometimes there's another queue where they can have like a response queue, right? They can just drop it in another queue, and then this client can check on the queue or with some type of ID to figure out if the task is completed. That's one way queue is used. It make it so that when you send a request, you don't necessarily have to wait to do something else. You can go do something else, and then you can check back to see if the task was completed by sending to the server, hey, this is my task ID, is it completed? Another way queue can be helpful is doing a service outage. Let's say, for example, this service goes down for some I don't know, reason that we're not aware. So since we're using a queue, the client can still continue working, right? It will send the request into the queue and then go do something else. Meanwhile, as the service, right, is down, like the queue is gonna keep on increasing in task, right? It's gonna be keep having tasks because they're not gonna be served. And then whenever this service go back online, then it's gonna go back and keep reading from the queue, and then it can drain the queue. There are other multiple ways that this can be useful. For example, if you have a service, and then if the service is reading from a queue, and for some reason, if the service goes down, right, the client can still continue working. The client would still just put more tasks into the queue, keep putting more tasks into the queue. And whenever the service that is reading from the queue go back online, then he can go and start reading from the queue to get his task done. There are many systems that leverage that task and queue at a proportionally like bigger level. But conceptually, I just wanted you to know that it exists, right? Like some of them, example would be PopSub is a very, very popular one. So this video was really long. That's my first time trying to do content like this. I hope you learned something, or if you didn't learn something, I hope you refreshed your understanding of some key distributed system. If you have questions, drop it in the comment. If you have some correction from what I've seen that I have said that you may feel like you can add some more context, you can also drop it in the comment. I will link in the description the paper that I used to create this video. And hopefully in my next video, I will try to be a little bit more concrete. I will use Google Cloud where we can see these components in real life. For example, we're gonna try to create a load balancer using Google Load Balancer. We're going to try to have server behind the load balancer and then try sending requests to it. If this type of content is something that you are interested, you should definitely subscribe to this channel. And also I will try to make some measurement so that when I say something is faster than something else, we can have some concrete measurement to see that in real life. Thank you very much. I hope you gained some value into this. It took me a while to create this one, and I wanted to try something new to the channel. Leave your comment, like this video, share this video, and I will see you next time. Peace.